Hello, grade 11s. In today's lesson, we're going to be looking at percentage yield and those limiting reagent and excess reagents. So without any further ado, let's have a look at this question here. So we have 5.2. It says the following balanced equation represents a redox reaction in which 8 grams of iron 3 oxide Fe2O3 reacts with 3.8 grams of aluminum, and then we are given this chemical equation here. So they say the reaction runs to completion, and then 5.2.1 says define the term limiting reagent. So let's look at that definition for 2 marks. So limiting reagent, we say, is a reactant that is completely used up in a chemical reaction. So that is how you are expected to define it according to your CAPS document. Then 5.2.2 says which one of the limiting reagent, iron 3 oxide or aluminum, is the limiting reagent, right? Then justify the answer by suitable calculations, right? So okay, in terms of that, let's look at the 3 easy steps that we can do in order to perform that calculation. So we have Fe2O3, and then we are given that this has a mass of 8 gram, and also we are given the mass of aluminum, which is 3.8 gram, right? So I just want us to look at the steps here. Step number one is to calculate the number of moles of each compound, right? So first step, the first thing that you want to do is to calculate the number of moles of each compound. So we have the mass of Fe2O3 is 8 gram, and then the molar mass here, Fe is 56, so that's 56 times 2 plus 3 times 16, and that will give us 160. And then punching this in our calculator, we have 0.05 mole, right? Now let's calculate the number of moles of aluminum. So we have N is equals to M over big M, and then we have 3.8. The molar mass of aluminum is 27 from the periodic table, and then punching that in our calculator, we have 0.14 mole, right? Then the second step here is to now compare the ratios. Remember, from here we cannot just say the limiting reagent is Fe2O3 based on the fact that we see that it has a smaller number. Why can't we do that? It's because when we check here, we can see that the ratio is not the same. So for every 1 mole of Fe2O3, we need to have 2 moles of aluminum. So the sharing is not the same. This is more like when you want to make a sandwich. So for a sandwich, you need 2 slices of bread, but you only need like 1 slice of cheese or polony, right? So the ratio is not the same. So for every 2 slices of bread, you only get to use 1 slice of polony. So this is what is happening here. Then step number 2, let's use ratios. So use ratios to find the required number of moles. The required number of moles. So remember what you just calculated in the first step here. These are the available number of moles, or as we would call them, the actual number of moles, right? So these are the actual number of moles. Then here we are calculating the required number of moles, right? Then an analogy for this one, take that you have maybe 16 slices of bread, but then you have 10 slices of polony, right? Then in this case, because we know that in order to make a sandwich you need 2 slices of bread, we know that here the maximum number of sandwiches that you'll be able to make, looking at the number of slices, would be 8, because now remember, 1 sandwich is made out of 2 slices. So we would only be able to form 8, or to make 8 sandwiches, right? Then, but how many slices will we have to use of polony to make 8 sandwiches? We would have to use 8 slices of polony. That will leave us with an excess number of polonies, that is 2, and then only 8 get to be used. Then that tells us what the limiting reagent is all about. Number one, the limiting reagent will tell us about the maximum number of products that can be formed. And number two, it tells us the amount of the other product that we need to use, or the other reactant that we need to use. Then in this case, we can use that ratio to say Fe2O3 to the ratio of aluminum is 1:2. Right, so the number of moles of this is 0.5, and then how much of aluminum is required for 0.05 moles of Fe2O3? We just cross multiply here, and then our X will be 0.1 mole. So we only need 0.1 mole of aluminum, but what we actually have is 0.14, which proves to us that aluminum is in excess. Why? Because the number of moles required are actually less than the number of moles that are available, right? Then this proves to us that aluminum is in excess, and then Fe2O3 has to be the limiting reagent. So we can say Fe2O3 is the limiting reagent, right? Because in a chemical reaction, if one is the excess reagent, then the other one is the limiting reagent. Hope it makes sense. 5.2.3 says, hence or otherwise calculate the percentage yield if 4.76 gram of iron was formed. Right. So what is this? This is the actual yield of iron. So it's 4.76 gram. Then we are required to calculate the percentage yield. But before we do that, let's look at the formula for percentage yield. So percentage yield is equals to the mass of the actual yield over the mass of the theoretical yield. And then you need to multiply that by 100, right? So this will be expressed in a form of a percentage. So percentage yield is equals to the actual yield over the theoretical yield multiplied by 100. Now we can see that we are given the actual yield. It's 4.76 grams, right? So that means in this case we have to calculate the theoretical yield, right? Now how do we calculate the theoretical yield? It's very simple. Now that in 5.2.2 we've already identified that Fe2O3 is the limiting reagent. What do? We simply compare the ratios of Fe2O3 to the ratio of iron. And then looking at our balanced equation, we can see that the ratio is 1:2. Right, so we can simply use that to calculate the number of moles of iron. So we have 1:2, but the number of moles we had here, the available number of moles was 0.05. Then here it's X. Then cross multiply here, we'll have 0.1 mole. So this represents the number of moles of iron. But then from here, we need to calculate the mass of iron, because remember, to calculate the percentage yield, we do not make use of the number of moles, but we make use of the mass, right? So now to calculate the mass of Fe, we will say N is equals to M over big M, right? And then what is our number of moles? It's 0.1. Then we're looking for the mass. Substitute in the molar mass of Fe, which is 56, and then when we cross multiply here, we have 5.6 grams, right? Now from here on, we can calculate the percentage purity by simply saying, or the percentage yield by simply saying percentage yield is equals to the mass of the actual, which was 4.76, and the mass of the theoretical yield, which is 5.6, the one we just calculated. Then multiply that by 100, our percentage yield is equals to 85%. And so we have 7.2 here. It says when heated, lithium reacts with nitrogen to form lithium nitride. And then we are given the balanced equation is 6 atoms of lithium plus nitrogen gas to give us 2 atoms of lithium nitride, right? And then we are given that 12 gram of lithium is heated with 33.6 gram of nitrogen gas. Then 7.2.1 as expected, it says define the term limiting reagent for 2 marks. Then we say limiting reagent is the reactant that is completely used up in a chemical reaction. Then 7.2.2 says determine by calculation which substance is the limiting reagent, right? So which substance is the limiting reagent? Again, we're gonna follow the steps that we just discovered, but then first thing is let's mark our data. So we are given 12.3 gram of lithium, and then we are also given 33.6 gram of nitrogen gas. So now we know the first step here, step number 1, is to calculate the number of moles of each compound, right? Then we have lithium. So to calculate the number of moles of lithium, that's N, small m over big M. And then what are we given? We are given that it is 12.3. So we have 12.3 divided by 7, and then the number of moles that we'll have there is 1.76 mole. So we divide it by 7 because lithium is the atomic mass of lithium in the periodic table is 7. Then now let's look at nitrogen gas. So we have N, small m over big M, and then what are we given as the mass? We were given that it is 33.6, and then divide that by 28. Why? Because nitrogen is 14 in the periodic table, but now we have 2 atoms of nitrogen, so that's 28, right? Then that divided by 28, it's gonna give us 1.20 mole, right? So we are done with the first step, but then we cannot conclude from here that nitrogen gas is the limiting reagent because the ratios are not the same. As we can see here, the ratio of lithium to nitrogen gas is 6:1. So for every one mole of nitrogen gas, we need 6 moles of lithium. So therefore we need to compare that ratio. So step number 2 is to calculate for the required number of moles. Calculate for the required number of moles using ratios, right? Using the coefficient ratios. Then we have lithium to nitrogen gas, but as we can see here, the coefficient of lithium is 6 and the coefficient of nitrogen gas is 1. So here we're gonna have 6:1. Now the rule of thumb with this one is just to take the number of moles, the available or the actual number of moles of your first compound that you'll have calculated here. So let's erase, let me write. So remember, these are the actual number of moles. What we have here are the actual number of moles or the available number of moles. So the rule of thumb is to take this one, put it here, 1.76. So now what are we trying to do? We are trying to find the number of moles of nitrogen gas that will be needed to react all of this 1.76 mole of lithium. Now in finding that, we want to compare it with this available number of moles, see if what is required is more than what we have available or less than what we have available. So now it's just a matter of cross multiplying here. So 6 times x, that's gonna give us 6x, and then 1.76 multiplied by 1, it's 1.76. Then we divide both sides by 6 so that we find x. Then our x is equal to 0.29 mole. So mind you, this is the required number of moles of nitrogen gas. So required number of moles of N2. Now, if this is what is required to react all of this 1.76 mole, then let's check nitrogen. Is nitrogen in excess or is it the limiting reagent? We can see that the available number of moles of nitrogen gas is 1.20 mole, and we are only required to react 0.29 mole, which proves to us that nitrogen gas is in excess, right? Why? Because the number of moles required is actually less than the number of moles available, or the actual number of moles, right? Which then proves that lithium has to be the limiting reagent. So therefore, lithium is the limiting reagent. And just like that, you have your solution. In 7.2.3, we have a next statement above here. It says the actual yield of lithium nitride in the above reaction is 5.89 gram. Then 7.2.3 says calculate the percentage yield of lithium nitride, right? So in order to do that, let's first write the formula for percentage yield. So we have percentage yield is equals to the mass, which is known as the actual yield, over the mass, which is known as the theoretical yield, right? And then you'll have to multiply that by 100. Okay, so now reading from the statement, we can see that we are given here the actual yield. The actual yield of lithium nitride in the above reaction is 5.89 gram. That means we have to now calculate the theoretical yield. But how are we going to calculate the theoretical yield? From here, we can see that in 7.2.2, we had already calculated the limiting reagent. Now, the limiting reagent has a very great bearing in you having to find the percentage yield. So, okay. Now, remember the limiting reagent, number one, it tells us of how much of the other reactant will be needed to react it with, right? So as in this case, we had this 1.76 mole, and then we had 1.20 mole available of nitrogen gas. But then in order to know how much of the nitrogen gas is needed for this reaction, we now use the ratios of lithium to nitrogen gas, and then we found that the required number of moles of nitrogen gas was actually 0.29 mole. So out of this 1.20 mole, we only needed 0.29 mole of nitrogen gas. How were we able to find that? Using the limiting reagent. Now, not only does the limiting reagent tells us about the reactant or the amount of reactants that we need to have, but it also tells us the amount of products that will be produced. So the maximum amount of products that can be produced from a particular reaction. Right, so in this case, now that lithium nitride is the product that needs to be produced, or the product that is produced, we can say now let's find the number of moles of lithium that can be produced, lithium nitride that can be produced, by using the ratio of lithium to lithium nitride. Now, if we look at the balanced equation, we can see that the ratio is 6:2. So let's use that. We have 6:2. But what is the number of moles of lithium that is available? We can see it from here. It's 1.76, right? So now let's use it here. We have this 1.76, and then here we have X, right? Now let's try to calculate the number of lithium, number of moles of lithium nitride that are produced. So that's 6 times X, 6X, then 1.76 multiplied by 2, and then divide by 6 both sides. So the number of moles of lithium nitride is 0.59 mole, right? Now at this point, what do? We try to calculate the mass of the lithium nitride, right? Because remember, in order to calculate the percentage yield, we need the mass and not the number of moles. So to calculate the mass of lithium nitride mass, let's have N is equals to M over big M. So substitute in our number of moles and then substitute our molar mass, which is 7 times 3 plus 14 is 35. So we substitute 35 here, then cross multiply here. Our mass is 20.65 gram. But then in order to calculate the percentage yield, we now have to say percentage yield is equals to the actual yield, which from here we can see that the actual yield is 5.89, right? So we have this 5.89 over the theoretical yield. So this is our theoretical yield. So this is the maximum mass that can be produced from this reaction. So this is 20.65, then multiplied by 100. Then punching that in our calculator, we have 28.52%. So the mass that was produced from this reaction was 5.89 gram. But the maximum mass that could have been produced was 20.65 grams. So the percentage yield is actually the percentage to look at the number or the mass that was produced versus the total or the maximum mass that could have been produced. So we find that from what was produced versus what we can potentially produce, it is only 28.52% that we were able to produce. Also, question 7, it says the fertilizer ammonium sulfate, which is NH4,2SO4, is produced from the reaction of sulfuric acid, H2SO4, and ammonia, NH3, according to the balanced equation. So we are given this balanced equation here, as we can see. Then they say 2 kg of sulfuric acid and 58.82 moles of ammonia are available to produce the fertilizer. 7.1 says define the term limiting reagent. So we say limiting reagent is the reactant that is completely used up in a chemical reaction, right? Then 7.2 says calculate the maximum mass of ammonium sulfate that can be produced by the reaction, right? So now I want you to pay attention to the choice of words by the examiner here. Said the maximum mass of ammonium sulfate that can be produced by the reaction. But what is this? Now the examiner chose to go the long way. He could have easily said calculate the theoretical yield of ammonium sulfate, right? So now I want you to know that the maximum mass of ammonium sulfate, or the maximum mass of any compound that can potentially be produced in a reaction, is actually the theoretical yield, right? So now the examiner can either say calculate the theoretical yield of, or he can say calculate the maximum mass of, right? So now you have to note all that. Now going back to the statement, we can say that we are given 2 kg, which we know that we need to convert this, right? So how do we convert kgs to grams? Because in chemistry we want our mass in grams, right? So we know that we multiply that by 1000. So this will give us 2000 grams, right? Then this is of sulfuric acid, and we are given 58.82 moles of ammonia. Then you can see that the information that we are given here is on the reactants. So you need to note this. In order for you to calculate the theoretical yield, you will first need to find which one of this reactant is the limiting reagent. So you will never get to theoretical yield unless you first get which one is the limiting reagent. So what you need to do here is to calculate the limiting reagent, or determine the limiting reagent by means of a calculation, and then you can use the limiting reagent to find the theoretical yield. So now let's go about that one. So step number 1 here is to obviously calculate the number of moles, right? So in this case, we won't be saying the number of moles of each because we are given the number of moles of ammonia. So we'll just calculate the number of moles of sulfuric acid. So we have mass over molar mass, and then that will give us 2000 divided by 98, which punching that in our calculator, we have 20.41 mole, right? Then what is the number of moles of ammonia? We already have it, so it's 58.82 mole, right? Then we know in order for us to determine which one is the limiting reagent, we cannot just simply look at these numbers and say sulfuric acid is the limiting reagent. We first need to confirm that. How do we confirm that? By calculating for the required number of moles of NH3. So this is the number of moles of NH3 that we have available. These are the actual number of moles. But now we want to know how many of the ammonia moles do we have to react with all this 20.41 mole of sulfuric acid. So we'll say H2SO4 to ammonia. And then now let's have a look at the ratio. We can see that the ratio here is 1:2, right? So looking at our balanced equation here, you can see that the ratio is 1:2, right? Then now let's use that. We have our ratio is 1:2. The number of moles of sulfuric acid is 20.41. And what is the number of moles of ammonia? That's what we are looking for, the number of moles that we have to react. Then if we cross multiply here, we find that it's 40.82 mole. So the required number of moles of ammonia is only 40.82, but the number of moles available for ammonia is 58.82. What does this tell us about ammonia? It tells us that ammonia is in excess because we actually have more than what is required. So we have more available than what is required. Therefore, we can say in conclusion, NH3 is in excess, right? Therefore, if NH3 is in excess, then it goes without saying that H2SO4 sulfuric acid is the limiting reagent. Why? Because in a chemical reaction, if one is the excess reagent, then the other one has to be the limiting reagent. You cannot have two limiting reagents or two excess reagents. So it's either one is that and the other one is the limiting reagent, right? Then, okay, so now that we have the limiting reagent, let's not get carried away with this. Remember, the question here of interest is to calculate the maximum mass of ammonium sulfate, which is the product. Remember, theoretical yield refers to the product, right? So now, how does us getting the limiting reagent help us in answering this question? Remember, if we now have the limiting reagent, we have to take the limiting reagent and compare it to the product in question, right? So we have this SO4. Then what is the ratio of sulfuric acid and ammonium sulfate? We can see it's 1:1, right? Then what does this tell us? It tells us that the number of moles of ammonium sulfate and sulfuric acid has to be the same, right? So if we have 20.41 here, we also have 20.41 here, right? Then now to calculate the theoretical yield, which is actually the mass of the ammonium sulfate, we have 20.41 is equals to M. And then what is the molar mass of ammonium sulfate? So using your periodic table, you will find that it's 132. Then cross multiply here, your mass is going to be 2694.12 gram. And just like that, you have your theoretical yield, which is the maximum number of ammonium sulfate that can be produced from this reaction. Awesome. Okay, so we have question 7. It says industrially vanadium metal V, which is used in steel alloys, can be obtained by reacting vanadium pentoxide V2O5 with calcium at high temperatures. The balanced equation for the reaction is as follows, right? Then let's just jump to 7.1. It says, state the definition of a limiting reagent. So what is that? We say limiting reagent is the reactant that is used up completely in a chemical reaction. So by now you should know that. Yeah. Then 7.2 says, calculate the theoretical yield of vanadium. So we want to calculate the theoretical yield of vanadium, which is the product. But then remember, what is theoretical yield? This is known as the maximum mass that can be produced, right? So this is the maximum mass that can be produced, right? Then, but then we know that in order for us to calculate the theoretical yield, we will first have to solve the issue of which one of these two reactants is the limiting reagent, because we cannot calculate the theoretical yield unless we know which one is the limiting reagent, so that we have to use that limiting reagent to find the number of moles of the product vanadium and then the mass, right? So now, which is why we are given this information. When we read here, it says during an industrial process, 1,850 grams of vanadium, which is a reactant, reacts with 2 times 10 to the exponent of 4 grams of calcium, which again is a reactant. So the first thing that we have to do here is to find the limiting reagent, and then from finding the limiting reagent, we can then calculate the theoretical yield, right? So now let's start. Our step number 1 is, of course, to calculate the number of moles, right? So calculate the number of moles of each reactant, right? Of each reactant. So the first reactant that we have there is vanadium pentoxide, which we're going to calculate as small m over big M. Then what is the mass we were given? 31,000. So this is 31,850. And then what is the molar mass? It's 182. So if you make use of your periodic table and then punching that, you have 175 mole, right, of vanadium pentoxide. But now let's calculate the number of moles of calcium, right? So we have small m over big M, and then our mass here is, we were given that it's 2 times 10 to the exponent of 4, right, which it's 20,000. And then what is our molar mass for calcium? It's 40, right? Then when we calculate here, we find that our number of moles is 500 mole. But then remember, we cannot just conclude from here and say that vanadium pentoxide is the limiting reagent because it has a small number. Now, why? Because if we look at the ratios, it is not the same. So for every 1 mole of vanadium pentoxide that we put out there, we actually need 5 moles of calcium, right? So now what are we supposed to do? Let's use ratios. So step number 2, let's use ratios to find the acquired, right? To find the required number of moles, right? Then we do that by simply taking the ratio of vanadium pentoxide, compare it with the ratio of the other reactant, calcium. And then now what is the ratio there? The ratio is 1:5, right? As we can see from here, right? Then the number of moles of vanadium pentoxide is 175. Now we want to know how many of the calcium moles do we have to react to 175 moles of vanadium pentoxide. So when we cross multiply here, we find that that's 175 times 5. So let's calculate that. 175 times 5, we find that it's 875 mole. So this is required of calcium, right? So we require 875 moles of calcium to actually react with only 175 moles of vanadium pentoxide. But what do we have available? you can see that when we check at the number of moles available, or the actual number of moles, the available number of moles is actually less than what is required. Then what does that tell us about calcium? It tells us that calcium is the limiting reagent. So Ca is the limiting reagent, right? And then obviously in this case, vanadium pentoxide will have to be the excess reagent. So you see, if you had simply looked at the numbers here, you could have assumed that vanadium pentoxide is the limiting reagent because of the small number. But then when you now compare in terms of the ratios, you actually find that as small as the numbers are, vanadium pentoxide is actually the excess reagent, and calcium here is the limiting reagent because it actually has less than what is required, right? So now we have Ca is the limiting reagent. Now let's use that to actually now calculate the theoretical yield, right? So how do we now calculate the theoretical yield? Remember, now we have to say the ratio of the limiting reagent to the ratio of what we are actually looking for, which is vanadium, right? So it's V. So the ratio there, calcium is 5, and then vanadium, the ratio is 2, as we can see here. Calcium, the limiting reagent, has a ratio of 5, and then this one a ratio of 2, right? So now let's calculate. Now what are we going to use? We are going to use this number of moles. We cannot choose this number of moles because remember, this is not what we have, right? This is what is required, but we only have 500 moles available. So we put 500 here, and then we put our X here. So what are we trying to find? We are trying to find the number of moles that will be produced of vanadium. Then doing this one, we have 5 times X is 5X, and then 500 times 2, that's 1000. Then if we divide both sides by 5, we find that our number of moles for vanadium is 200 moles, right? So we have 200 moles being the number of moles of vanadium, right? So to calculate now the theoretical yield, so let me make space here. So now calculate the theoretical yield. Hope you will follow through. So now calculate the theoretical yield. What do we need to do? We take this number of moles of vanadium, and then we calculate the mass. So we have this 200 here, and then M. But what is the molar mass of vanadium from the periodic table? So looking up vanadium from the periodic table, we find that it is 51. So the theoretical yield, or the maximum mass of vanadium that can be produced, is actually 10,200 grams, right? So that is the maximum number of that is the maximum mass of vanadium that can be produced, right? Then calculate the percentage yield if 8.67 times 10 to the exponent of 3 gram of vanadium is obtained. Now this one is straightforward because it's just a matter of now saying percentage yield is equals to, so yield is equals to the mass of the actual yield over the mass of the theoretical yield, which we have now calculated in 7.2, and then we have to multiply that by 100, right? So what is the mass? We are given that it is 8.67 times 10 to the exponent of 3. Then what is the theoretical yield? It's 10,200. Then multiply that by 100. You punch your calculator. So this is 8. So if you punch your calculator, you find that the percentage yield is 85%. And that's how you go. Awesome.